Hello. In this video, we are going to derive the vibrations of water, H₂O, using the projection operator method. We note that water belongs to the point group C2V, and we draw a quick sketch as the first step in the solution of our problem. Note that water having three atoms can be confined to a single plane, so it is planar, and we set it up so that the high-order rotation axis, the C2 of water, is the z-axis, and that is going up on our board, and the x-axis is going to the right. The remaining y-axis is coming out of the plane of the whiteboard. The next step in the derivation of the vibrations is to form a reducible representation for all 3n degrees of freedom for H₂O. So we can make a small chart, and we have a column for each of the classes in the point group. And it turns out in C2V that each operation belongs to its own class. So we have one column for each of the four symmetry operations in C2V. For the first line, we want to make a reducible representation for the atoms that don't move under each symmetry operation. Atoms that don't move is a good description of this particular representation. Under the E operation, all three of the atoms in the molecule remain where they are, so the character for this particular representation is a 3 for the E operation. The C2 operation goes around the z-axis, takes this hydrogen to that hydrogen, this hydrogen gets moved over to here, but the oxygen atom stays where it was, which is always really true when we have something that sits exactly on the symmetry operation. So here we have one atom that doesn't move. Next, we have a vertical mirror, sigma v, in the xz plane, which we notice is the plane of the whiteboard. All three atoms are sitting on that symmetry element, so they're not affected by it. So again, we have a character of a 3 for sigma v xz. The fourth and final symmetry operation of water is sigma v yz, which is a mirror plane coming up like this, perpendicular to the whiteboard. That reflects each of the hydrogen atoms into the other, so each of those would move. But again, since the oxygen atom is on the symmetry element, it is not affected by it. Or another way to come to the same conclusion is we can realize that the mirror operation would reflect oxygen into itself. So again, we have one atom that does not move. So we have completed the first line of our table. For the second line, here we have another representation, and this gives us the values of the trace for the 3x3 matrices that define each of these symmetry operations. The trace is just the sum of the entries along the diagonals of that 3x3 matrix. For E, E has 1s along the diagonal. It has 1, 1, and 1. So the trace for the E matrix, which is the same as the identity matrix in R3, is 3. For C2, the entries along the diagonal are -1, -1, and +1. Therefore, the trace of the C2 rotation matrix is -1. For sigma v, one rule we can remember is that the mirror planes will have matrices that have a 1, a 1, and a -1 in some combination along the diagonal. So the trace for a mirror plane will always be plus 1. So using that knowledge, we can put down that the trace here is going to be 1, the trace there is going to be 1. So the overall value of the reducible representation for all 3n degrees of freedom for water we get by multiplying the character in the second row times the character in the first row for each of the classes of the point group, which work out to be equal to each of the symmetry operations for the point group. 3 times 3 is equal to 9, so our character is a 9. Minus 1 times plus 1 is minus 1, so our character is a minus 1. 1 times 3 is equal to 3, and 1 times 1 is equal to 1. So we have been able to derive a reducible representation that describes all 3n degrees of freedom for our molecule water. Next, we want to reduce our reducible representation to a linear combination of irreducible representations within the point group C2V. So recall that we have to look for each of the irreducible representations separately, one at a time. So we start off trying to figure out how many A1 irreducible representations are included in this reducible representation. And recall that the factor we put in front of all our terms is 1 over the order of the group. The order of the group for C2V is 4 because there are 4 symmetry operations in the group. So we have 1 divided by 4. And then for each term, we have 3 factors. The first factor is the number of operations in the group. We notice that there are no coefficients in this particular character table, and this implies that there is there's a 1 here, which is omitted just for brevity, but we'll put the 1 in there just to show the procedure, because in many point groups you will find classes that have more than one symmetry operation. So the first step is the number of operations in a particular class. So that's where the 1 comes from. The second factor in each term is going to be this character from the reducible representation. So that is a 9. And the third factor, which we'll write in green here, is the character from the character table that applies to the irreducible representation. So for A1, the character for this symmetry operation is a plus 1. So 1 times 9 times 1. And we do each of these terms for each class of the point group. So again, 1 operation. The character from the reducible representation is a minus 1. And the character from the character table is a plus 1. And we could work out A1 without even consulting the character table for C2V, since we know that A1 is the totally symmetric representation, so the characters for each class are going to all be 1s. So next, for the first sigma V, there is 1 operation in the class. The character from the reducible representation is a 3, and the character from the character table is a plus 1. So that gives us 1 times 3 times 1. And then for the fourth operation, there is 1 operation in the class, so that gives the 1. The character from the reducible representation is a 1, so that's the 1 that comes there. And then we need a 1 from the character table, and that gives us a 1. So now we work out this particular sum. So we have 9 minus 1 plus 3 plus 1. So that gives us 12. 1/4 of 12 is equal to 3. So this tells us that there are 3 A1 irreducible representations included inside this reducible representation. An important fact is that when we figure out how many irreducible representations are stored inside the reducible representation, the answer always has to be either 0 or a positive integer. If you ever get a negative number or you get a fraction or a decimal. That cannot possibly be true. So if that happens, the most likely cause is an arithmetic error of some sort. So next, we do the same procedure to see how many H₂ irreducible representations are stored within this reducible representation. So you have 1 divided by 4. And one thing which makes our work go much more quickly is we realize that for each of the irreducible representations, for each of these terms, the first two factors, the one, which is the number of operations in the class, is always the same for this particular operation. And the character from the reducible representation will always be the same. So the only factor that we need to change in each line is the third number in each of these terms. Because this particular value, the positive ones that are in green here, are from the character table for the irreducible representation A1, and then in this case we need the characters for A2. So we will rather quickly write down the first two terms and then we have to put down the character from the character table. So for A2, the character in the character table for E is also a +1. Now for C2, there is one operation in the class. The character from the reducible representation is -1. And the character from the character table for A2 is again a +1. So far it looks as if A2 is going to be identical to A1, but we'll see that soon it will not be the same. So when we get to the third symmetry operation, the sigma v, again there's one operation in the class. The character from the reducible representation is A3. But now the character from the character table for the irreducible representation is a -1. And then for our final symmetry operation, the last sigma v, there is one operation in the class. The character from the reducible representation is a 1. And then the character from the character table for the irreducible representation is a -1. So now for A2, we see that we have 9 -1 -3 -1. So that gives us 4, so 1/4 of 4 is equal to 1. So we see that there is one A2 irreducible representation that is stored inside of gamma 3n. The third irreducible representation in point group C2V is B1. So we can figure out how many B1s are included in the reducible representation, again by using our reduction formula. 1 times 9. And then the character in the character table for C2V, for E, for B1 is again a +1. Operation C2, there's one operation in the class. The character from the irreducible representation is, for the reducible representation is -1. The character from the irreducible representation, from the character table, is a -1 here. Next, for the first sigma v, there's one operation in the class. The character from the reducible representation is a 3. The character from the character table is a +1 for B1. And then for the final sigma v, there's one operation in the class. The reducible representation character is 1. And then the character from the character table for the irreducible representation is a -1. You will also notice that the third factor in each of these cannot be identical from A1 to A2 to B1. So each irreducible representation has a different set of these numbers. So the first A1, all the ones are positive. For A2, we have a positive 1, then a negative 1, and a negative 1. For B1, we have a positive 1, negative 1, positive 1, negative 1. So this gives us 9 plus 1, which is 10, is 13, minus 1 is 12. So we have 1/4 of 12, so we have 3 B1s included. And last but not least, we want to see how many B2s we have included in our reducible representation. So these are always the same, so I can put them in by rote. The second factor is always going to be the character from the reducible representation. So we know that's going to be 9, minus 1, 3, positive 1. Then the third factor is going to be from the character table. So the character for E is 1 for B2. The character for C2 is minus 1. The character for the first sigma V is going to be a minus 1. And then the character for the second sigma V is going to be a plus 1. So this ends up equaling 8. So we have that 1/4 of 8 is equal to 2. What we have determined is that we can write the reducible representation, gamma 3n, which describes all 3n degrees of freedom for water, and water has 3 atoms, n is equal to 3, so there are a total of 9 degrees of freedom. We found that those correspond to 3 A1s plus 1 A2 plus 3 B1s plus 2 B2s. And since each of these is a non-degenerate irreducible representation, each one counts as 1 degree of freedom. So here we have 3, 4, 5, 6, 7, 8, 9 degrees of freedom, which is exactly what we expect so far. So let us rewrite our current result so far, just to remind ourselves that it's 3 A1s plus an A2 plus 3 B1s and 2 B2s. And it's important to keep in mind that this describes all 3 n degrees of freedom, which includes translations, rotations, and vibrations, but we are only interested in the vibrations at the moment. So let's remove everything that has to do with translation, all the translational degrees of freedom. And we can recognize those in the character table for C2V as being those irreducible representations whose basis functions are x, y, or z. So we notice in the character table for C2V that the irreducible representation A1 has a basis function z. So therefore it's a translational degree of freedom. We see that B1 corresponds to a basis function of x, and that B2 corresponds to a basis function of y. So we subtract out anything that has to do with x, y, or z as a linear term. So this gives us 2 A1s plus A2 plus 2 B1 plus B2. Our next step is to subtract out everything that has to do with rotations. Subtract out all our rotational degrees of freedom. And these are even easier to recognize in the character table because these will be the irreducible representations whose basis functions have a big R sub x, a big R sub y, or a big R sub z, which are rotations about the x, y, or z axes, respectively. So we notice that the rotation around x, Rx, has B2 symmetry, so we use the B2 irreducible representation for that. For rotation around the y-axis, the irreducible representation is B1, and the rotation about the z-axis is A2. So if we subtract these irreducible representations from what we have so far, this will actually give us the linear combination of irreducible representations that describe vibration. So we see that we're left with two A1s and a B1. And we expect to have 3n minus 6 degrees of freedom for vibration. Water has 3 atoms, n is equal to 3. 9 minus 6 is equal to 3. So we have the correct number of vibrational degrees of freedom for water. In our next step, we will actually work out what the stretches and bends of water actually look like. For this portion of our derivation, we want to think of the oxygen-hydrogen bonds as vectors. So the rightmost bond we call the vector R1, and the second OH bond we'll refer to as vector R2. And we want to see is what happens to vector R1. We could use either 1 or R2 because we notice that these are interconverted by at least some of the symmetry operations of the group. So we say that these are symmetry equivalent. So we want to see what happens to a typical member, which is R1, under the various symmetry operations of the group. So for example, under the identity, R1 stays where it is, which is what the identity does. It turns to R1. If we do a C2 operation, remember that our C2 axis was along here, that flips the molecule over, so R1 turns into R2. For the mirror plane sigma xz, which is the plane of the whiteboard, that reflects R1 into R1. And last but not least, our last symmetry operation is a mirror plane perpendicular to the whiteboard. So that takes R1 into R2. Now we know that we have various types of stretches. We have A1 and we have B1. So let's first see what the A1 stretch looks like. So for A1, we make a row of our table, and under each symmetry operation, we put the character from the character table of the C2V for the irreducible representation A1. And we recall that A1 is the totally symmetric representation, so even without consulting the character table, we know that these characters all have to be positive ones. So we multiply these characters times the terms up here to get R1, R2, R1, and R2. And our vibration is a linear combination of all these entries. So we can simplify that for A1 as being 2R1 plus 2R2, and we can divide through by lowest terms, and this gives us R1 plus R2. And a way to interpret this particular vibration, since the coefficients of R1 and R2 are both positive, this is consistent with both bonds getting bigger at the same time and then getting smaller at the same time. So this is often referred to in spectroscopy as a symmetric stretch, because both bonds are getting larger or smaller at the same time. So we see that this is the A1 symmetry. We also have stretches of B1 symmetry. So let's make the appropriate changes to see what the B1 stretch looks like. So the character table for B1, the characters are +1, -1, +1, and then -1. So, and we multiply the character in the second row times the character in the first row. So 1 times R1 is R1, -1 times R2 is -R2. 1 times R1 is R1, -1 times R2 is -R2. So this tells us that this particular vibration is 2R1 minus 2R2, which again we can reduce to lowest terms as R1 minus R2. So for this vibration of B1 symmetry, the bond R1 gets bigger as the bond R2 gets smaller, and then they alternate. So this is consistent with what would be termed an asymmetric stretch. So we found both of the stretching motions for water, one of which has A1 symmetry and one of which has B1 symmetry. Our last step is to determine any bending motions, any changes in bond angles for water. We have one remaining degree of freedom, which is a bending motion of A1 symmetry. That is the last of the irreducible representations for which we have not determined what the vibration actually looks like. And the trick that we use for bending motions is to think of the bond angle from hydrogen, oxygen to hydrogen simply as a vector that bisects the angle between them. So, and we'll just call this vector B1. In more complicated molecules, we will have several bending motions, so we'll have lots of different vectors corresponding to the bond angles. But in water, there's only one bond angle that we have to consider. So we want to see, even if it seems rather trivial, but we can derive what happens with the bending motion under the various symmetry operations of the group. So under the identity, B1 stays put where it is. C2 goes around the same axis that B1 is directed along, so B1 is not changed. We end up with B1. The mirror plane of the plane of the whiteboard reflects B1 into B1. And sigma V, the mirror plane is perpendicular to the plane of the whiteboard, also goes through B1, so B1 is unaffected, so we have B1. So to figure out what happens under the A1 stretching motion, and A1 bending motion, apologies. Again, we multiply the characters in the first row by the characters from the character table for A1, and all those characters are positive ones because A1 is a totally symmetric representation. We multiply the values in the second row times the first row, and we notice we end up with just B1. So this can all be reduced to lowest terms as just B1. So in this case, there only is one bond angle. So the bond angle is going to get bigger and get smaller, and it's not synchronized to any other motions in the molecule. Therefore, using the projection operator method, we have been able to derive an A1 bending motion and an A1 and B1 stretching motions of water. I thank you very much for your attention. Have a good one.